How is it we should measure information in a way that applies to any communication system you can think of? Human, animal, or alien? Well, let's return to the late 19th century, where at the time we were focused, as we are today, on speed. And one goal to improve speed was to design a machine which allowed the operators to input letters, which we can think of as primary symbols, and have the machine automate the lower level signaling events, such as pulses of electricity, what we can call secondary symbols. And machines can be driven by some clock source, allowing it to generate a precise and rapid pulse stream, which presumably would run much faster than any human hand. And one great example of this was the Baudot multiplex system, and the design was put into service in 1874. And it built off the same conceptual ideas we've seen in the shutter telegraph. It consisted of 5 keys which could be played in any combination. Think of it as a chord. Each combination would represent a unique message. With 5 notes, each either on or off, you can play 2 to the power of 5 or 32 different chords. The code assigned the 32 different chords to each letter of the alphabet, with the leftover used for carriage returns, new line, and spaces. So the operator would literally play letters, and their machine would automatically output a pulse stream representing the letters.
Like this for letter T. Or like this for letter R. Or like this for letter B. So we have an output signal containing various combinations of DC impulses, a signal that accurately represents the message typed on the teletypewriter.
Behind the counter, the mechanical nerves of the system change words to holes on tape, and the holes on tape to electrical impulses speeding over the wires.
Notice at the lowest level, this system is exchanging either the presence or absence of electrical current in a sequence divided using a clock. So, how fast can our internal clocks run? Well, the limiting speed was not the clock. Then and today, the speed of transmission was physically limited by the minimum spaces between these impulses, or the pulse rate. And this problem plagued engineers who were testing underground submarine cables using the existing Morse code system. And it's similar to an echo or a sustained note. If one sends dots too fast over a long undersea circuit, they will run together at the receiving end. Because the symbol we receive at the far end of the circuit will be a slightly longer, smoothed out rise and fall, not an exact replica. And sending pulses too fast results in intersymbol interference. This occurs, for example, when the longer flow of a current bleeds into the next time division and perhaps reverses a 0 to a 1. So even if we are automating the detection of these current levels, there is a fundamental limit to how far we can squeeze 2 pulses together. And this is the same problem Alice and Bob ran into with their string communication system, which we called the maximum pluck speed. If they plucked any faster than 2 plucks per second, they noticed they started to bleed together and they got confused. So this is called the symbol rate. Remember, a symbol can be broadly defined as the current state of some observable signal, which persists for a fixed period of time. Whether you are using fire, sound, electrical current, anything, a signaling event is simply a change from one state to another. So the symbol rate is the number of signaling events which can be squeezed together in 1 second.